Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on thermodynamics. Previously, we discussed how isothermal, isobaric, and isochoric processes are related to the first law of thermodynamics. Today, we will be focusing on another type of process that occurs in gases, called the adiabatic process. If you are ready, we will begin. An adiabatic process involves no energy transfer into or out of a system as a result of heating. Thus, adiabatic processes occur because of changes in pressure. Adiabatic processes are quite common. One such example of this process occurs in a bicycle pump, as you see here. As the plunger rises and descends, air is pulled and pushed in and out of the nozzle. The pump is a steel cylinder with an internal piston. If a finger is held over the nozzle and the air is pumped, it becomes compressed. If the plunger is pushed hard enough while blocking the escape of the air will force its own way out. We can see that the mechanical work done on the air results in an increase in the internal energy of the air. There is no phase change, so the potential energy of the molecules stays constant, but the average random kinetic energy of the molecules increases. Applying the first law of thermodynamics, we can create an equation that reflects the adiabatic process. Since there is no heat transfer into or out of the system in this process, change in internal energy is equal to the negative of change in work done. Therefore, we can conclude that in the adiabatic process, an increase in energy is equal to an increase in work. Students, it is time for an activity. Here are two pressure volume graphs. Can you identify each? Once you have, which equations apply to each process? Lastly, why did these processes have this many similarities?
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, everyone. Were you able to answer all the questions correctly? Let us go through them together. The first process is an adiabatic process, while the second process is an isothermal process. As we introduced, the appropriate equation for the adiabatic process is delta U equals negative delta W. The equation for the isothermal process is delta Q is equal to delta W. These processes are very similar because they both involve a direct relation between volume and pressure. Thus, in either process, when volume is increased, pressure will decrease. Note that in an adiabatic process, there is no heat transfer into or out of the system. It happens very quickly. In an isothermal process, there is no change in the internal energy of the system. Let us try applying the first law of thermodynamics to a calculation. Imagine that ammonia gas is expanding rapidly within a cylinder, forcing a frictionless piston to move a distance of 10 centimeters. The process is isobaric, which means that the pressure of the gas remains constant at 130 kilopascals. The mass of the gas is 1,300 milligrams, and the area of the piston in contact with the gas is 3.0 times 10 to the power of -3 square meters. Bearing in mind that the specific heat capacity of ammonia at constant pressure is 2.2 kilojoules per kilogram Kelvin, what happens to the temperature of the ammonia? This is a tricky problem, so try to solve each step one at a time. Do your best, and I will see you in a few minutes.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again. I hope that you did not have too much trouble with this challenging problem. Let us look at the answer together. The change in volume of the gas is expressed by the equation 3.0 times 10 to the power of -3 square meters times 0.1 meters. This equals 3.0 times 10 to the power of -4 cubic meters. The mechanical work done on the piston by the gas is equal to the pressure times the change in volume. So we can write it as 1.3 times 10 to the power of 5 pascals times 3 times 10 to the power of -4 cubic meters. Therefore, the work done is equal to 39 joules. The process is very nearly adiabatic, so we can say that the increase in internal energy of the system equals the amount of work done on the system, which in turn equals the negative constant pressure of the gas times its change in volume. This is -39 joules. We have learned that the increase in internal energy equals the mass of the gas times its specific heat capacity times its change in temperature. Since we are trying to solve for the change in temperature, let us rewrite our formula as delta T equals delta U over MC. Now, all we have to do is substitute the correct values. -39 joules over 1.3 times 10 to the power of -3 kilograms times 2,200 joules per kilogram Kelvin. This simplifies to -39 joules over 2.86 joules per kilogram Kelvin. Therefore, our answer is -13.64 Kelvin. The temperature of the ammonia gas has decreased by 13.64 Kelvin. Did you manage to get the same answer? If so, great job. If not, review this question after the lesson to be sure you understand all of the concepts. That is all for today. We have studied the concept of an adiabatic process and have applied it to solve problems involving the first law of thermodynamics. Great work today. Until next time, thank you, teacher. Thank you, students.